Hi guys, like Tim said, my name is Mitch, and I'm really happy to show you one of our newest products called the Quanser Aero. So as you can see on your webcam, I'll just basically give a high level introduction of the system, and then we'll get to the hardware, so the actuators and sensors on the Aero, and how to run it, right? Different software uses, and then then I'll give you a couple of demonstrations of the controllers that we have. So the Quanser Aero is a 2 degree of freedom aerospace device with two rotors. So you have the pitch axis here and the yaw. Some of the things that we're going to highlight as well is you can change the configurations of the system by changing the angles of the propellers and by locking the pitch and yaw axes, right? So that allows you for different aerospace configurations. So we'll go through that. We're also introducing a new QFLEX 2 interface, and that allows you to have some. It's a very innovative concept, and something we're going to start using for many of our new systems that we'll be launching. And that allows you to have, for example, a USB connection and even like an embedded microcontroller interface. So let's get to the hardware in a bit more detail. So we have, this is the main or the front rotor that predominantly in this configuration, right now I have it in the DOF Helicopter setup. This will control the pitch predominantly. And then we have the tail rotor, which is the yaw. So the propellers, the rotors are in there, are the ones I have here. So those are the ones that are shipped with the system. Those are kind of the, I guess you could call them the default propellers that come with the Aero. Each rotor is driven by a DC motor. So you have full access to the voltage of each of those motors. Now we'll also be supplying another set of blades that are more high efficiency but have less coupling as well. So we'll have so it'll be two different sets, right? But right now I'll just be using the standard rotors on the system. Now let's talk about the sensors. We have a total of 4 encoders. So as you can see, we have an encoder on each of the DC motors. We have an encoder there and an encoder here. We also have, so that allows you to measure the position of the DC motor, i.e. the rotor. And we have an encoder on the yaw and the pitch. So you can measure the position of the pitch axis and of the yaw. Now through the driver that we've developed for the system, so that would be under our Quark software, you can have access to the speed measurements as well. So there's like a digital tachometer that derives the velocity using those encoder signals. So it's like 4 sensors, including 4 digital velocity measurements. The other really neat thing about the Aero is we have an IMU. So we have an IMU that has a 3-axis accelerometer and a 3-axis gyroscope. So that allows you to do a number of other experiments such as attitude estimation and observer design. Now let's talk about different configurations you can do, and also, so as you can see here, the yaw has a slipper design that allows you to move it continuously 360 degrees. But you can choose to lock the yaw if you want using the Allen key. So if you want to conduct experiments only in the 1 DOF configuration, 1 degree of freedom pitch, then you can do that. You can lock the axis and just do that. Similarly, you can lock the pitch. You can also adjust the angles of each rotor. So we'll go through 3 different configurations today, so you can have an idea of how you can do that, how you can change between different configurations. There's an LED light here at the bottom. So right now it's in red, but it's user programmable, so you can change it from like red to green, for example, when you're running a controller. So that's basically what we have it set as right now. But it's so that's another nifty little thing that you can program. So let's talk a little bit about the QFLEX interface. So in the back here, I'm using the USB interface. So you can see here, I got a USB connection and the power connection that goes directly to it. So that is your data acquisition. That's your data acquisition system. The amplifiers are all built in. So it's a very integrated solution, very nice and compact. But you can have different interface panels for this QFLEX. So we have the USB that I'm using right now. So that's shown here. And we also have an embedded option if you're using an Arduino board, for example. So that's an innovative new concept that allows you to have some different interface options. In terms of software, so what I'll be showing today is our Quark software. So I'm really using the MATLAB Simulink environment and driving the system using the Quark Rapid Controls Prototyping software. We'll also have LabVIEW files as well, so they'll be fully compatible with LabVIEW VIs through the QRCP add-on that we've developed for the National Instruments LabVIEW environment. Okay, so I think we can, I think I've highlighted pretty much all the system description. Like Tim was also talking about in terms of who this applies to. As I go through the controllers, I think you'll find out more. It's definitely for the control system student, aerospace engineering, obviously, mechatronics, mechanical engineering as well. Mechanical engineers can have a lot, even like mechanical design. So there's a lot of different areas that this product can touch, and that can suit your educational and research needs. So on my screen here, I'm going to open up MATLAB, and we'll start with. What if you want to do pitch-only exercises? So right now we'll be working with the so-called, I guess, 2 DOF configuration, right? So that's like the traditional helicopter that you have, right? A main rotor and you have an anti-torque tail rotor, right? So that's the configuration we'll be using for the next like two, 3 demos. As you can see, there's an Allen key that locks into place using these magnets, right? So with this Allen key, I can choose to, for example, I can choose to lock the yaw, right? So there's, if I put the Allen key in here, so the Allen key fits through this, and then it locks into a little magnet here. So you can't really see it on the camera, but there's a little, in this little hub here, there's a little, there's a magnet that couples to the Allen key that I've pressed down onto the unit. So now, now you can see that it's locked into the yaw. So the yaw axis is totally locked, and I can conduct pitch-only exercises, right? So that could be used for control exercises, for example, or maybe I want to just estimate a parameter such as thrust, which is part of what we supply. So I'm just going to go through a simple controller here and show you basically what you can do if you wanted to find what the natural frequency or what the thrust is of about the pitch axis, right? So let's say you've identified a number of parameters, and now you want to apply an impulse. So in this MATLAB, in the Simulink diagram here, I would just apply an impulse voltage to the pitch, no voltage to the yaw, and then I would measure the corresponding the speed of the pitch. I'm using the IMU board here. So as you can see, if I zoom up a little bit so you can see a bit better, right? So I'm applying a voltage to the pitch, no to the yaw, no voltage, and then I'll be using the IMU board to measure the speed of the pitch. Now you could, of course, use the velocity measurement from the pitch. There's different ways to do it, but this is the method I chose. It's a nice smooth signal, so I'll be using that. If I go inside, this gives you a little glimpse of the I/O interface that Quark gives you, right? So you have, for those familiar, and we've done webinars, and we have material on our website if you want more information about Quark, but it has these supplies you Simulink blocks and a Quark targets library that allows you to access the gyro, the accelerometer, the tachometers, and the pitch and the yaw sensors. There's also current sensors, as well as like change the LED light and enable the motors and so on. Okay, so I'm just going to go ahead and run this. So it's just going to apply a small signal like this. And then you get a measurement, right? So based on this measurement, you can go and find, it also saves the data offline. So you can resupply, if you want to find the thrust of the pitch, you would run this and it would give you the response, right? This is a response that I got, that I obtained earlier on. And, but it, you can save data and all that stuff, and then use MATLAB figures to identify your values. So that's one simple example of what you could do just for a pitch only. So now let's switch gears and do the full 2DOF configuration, right? So if I want to go to 2DOF control, so I'm just gonna take the Allen key off. So I remove the Allen key and I put it back in here. So now the yaw is free to move again, and so is the pitch. So after you've identified the parameters and you found a model of, like a suitable model of the system, then you can design a controller to stabilize the pitch and the yaw. So let's go through the first one here. So I'm going to show you two approaches. The first one will be the PID control. So here I have on the screen control of the pitch and the yaw using using a PIV controller, which is basically a PID based controller for each axis. Now the thing is, with this configuration, with the 2DOF helicopter, there is a huge coupling effect, right? So you get these couple dynamics between the pitch axis and the yaw axis. So when I so for example, when I apply a voltage or torque to the pitch, that will also affect the yaw. So it'll actually create a torque along the yaw. Similarly, when I'm moving the yaw, so when I'm changing the torque, the rotor speed, the torque of the yaw, this will have an effect. It'll exude a torque on the pitch axis, right? So these two are constantly affecting each other. So the PID control, just something to take note is, it's a so when we do the control design, we consider each axis separately, right? So it's not a coupled controller, it's decoupled. So now I've got a set of gains in here, and I'm just going to go ahead and run it. So right now, the yellow here represents the set point, and the purple is the pitch measured from the encoder. So note that when it's changing in the yaw, which is a really big movement, I'm just going to stop this for a minute, then you'll see that in the pitch, you get a huge overshoot here, right? So this represents the coupling in here, right? So when the yaw moves, you get this huge motion in the pitch, and you should be able to see it on the screen. So here's the yaw encoder. So when the pitch moves, so you get these little perturbations, if you will, along the yaw, right? So the controller has to compensate for this. So these are the torques that are introduced from the pitch when you control the yaw, and these are the same that are affecting the pitch when you're moving the yaw. So let me run it again, and now that you've seen this. So you can see a bit of the oscillations, a bit of the overshoots, especially in the pitch. Okay, so I'll stop that. So that's one example of one approach you can do to control the 2DOF helicopter in both the pitch and yaw. And note as well as when I'm running the controller, the LED light was changing as well. So now let me show you a different approach. This is using a state feedback controller, which is a couple design. So the model that was based on deriving the gain, which we was using the linear quadratic regular method, or LQR, was based on a model that does have this coupling effect. It takes that into account. So now if I run this using the same set point, so a pitch and yaw set point are the same. I'm just going to go ahead and build this. So to give you an example of what we supply, some of the files, here's a state space model that we have, and then here is the LQR controller. So I'd run this and it generates my gain, and then I can go back to this and go Quark start to run the controller. And now let's see the difference in here. So I'm just going to expand the scopes. So now there's you'll see that when it's changing in the yaw or the pitch, there's a lot less perturbation, right? So because this is a coupled controller design, you get a much better performance, right? The tracking of the pitch could be improved, of course, but this is just a sample and example gain. But as it's moving in the yaw, you get way less perturbation along the pitch. So I think that gives you a second approach of what you can do. Again, the LED right now has changed color. I'm just going to go ahead and stop that. And again, you can save all this data, and of course, everything is totally open, so you can change around your controller. So for this one, you know, besides parameter estimation, which I've shown you, controlling, you can also do observer design using the IMU for like attitude estimation of the pitch and yaw. So there's a number of different things that you can do that you can progress from what we've supplied. Now I've shown you like locking the yaw. And I've shown you the full 2DOF when it's free to move in both the pitch and the yaw. The third configuration we'll go through is called the half-quadrotor. So in there, the half-quadrotor design, you're all familiar with the quadrotor system, right? Which was shown earlier on in the presentation. So quadrotor system will have all the propellers. So right now I've changed the angle of the tail rotor to point down as well. And next thing I want to do is I want to only focus on the yaw. So by tightening up these two, I can lock the pitch, right? So I'm just going to move this out of the way for a minute. And tighten this a bit. And tighten the other guy. So that should be good enough. So right now it's locked in the pitch, and it's allowed to move in the yaw. So this is like this configuration is basically the half-quadrotor with the pitch being locked, right? So it's a yaw-only quadrotor system. So again, developed the model for this, and we have two approaches: PID and state feedback using LQR. Also, we'll be having we have a Kalman filter design to estimate the attitude of that. So let's go ahead and run that. So I'm gonna just go straight to the LQR design here. Again, we have a number of scripts that we supply. So half-quadrotor design, and we'll be changing the yaw plus or minus 45 degrees. So here is the quarter right there. So it's doing pretty good tracking. Both the pitch and yaw have the same voltage, right? Because of the way the propellers are oriented, then you send the same signal. So this is actually using this cross torque effect to move it about the yaw. Now, what's great about this system is it's a great segue. It's like for students and researchers like to study certain phenomenon of a full quadrotor, but just focusing on one part of the system. So again, it's a huge advantage of the Aero. So that's a third configuration that you could do with this. Of course, you can free up the pitch axis to make it more complex and do some observer design or anything else with that. And that about wraps it up in terms of the demos and the hardware. So yeah, I'll throw it back to Tim if you guys have any questions.